Part A asks to prove the trig identity of sine x plus y times sine x minus y equals sine squared x minus sine squared y. First, we need to decompose the left-hand side into sines and cosines that only involve x and y instead of compound angles. We can do this by looking at the formula booklet for the compound angle identity formula. So, in the formula, we can replace a and b with x and y. So now we can rewrite the left-hand side as the product of two identities. We can now use the FOIL method to expand the brackets. The two middle terms cancel each other out, so we're left with sine squared x cosine squared y minus sine squared y cosine squared x. So now we need to somehow get rid of this cosine, since our answer needs to be only in terms of sine. So for this, we can use the Pythagorean identity found on page 6 in the formula booklet. So we can rewrite it as cosine squared equals 1 minus sine squared. So now we're able to replace cosine squared y and cosine squared x with just sine squared. We can now expand the parentheses. And now two of the terms cancel out. So in the end, we're left with what we were meant to prove: sine squared x minus sine squared y. Part B gives us a function f of x, which is sine x plus pi over 6 times sine x minus pi over 6 over the domain 0 to pi, and it asks us to find the range of this function. The first thing we should do is try to find a connection between part B and part A. In this case, we see that part B is written in exactly the same form as the trigonometric identity we proved in part A. This means we can rewrite this function f of x as the identity in part A. So we can rewrite it as sine squared x minus sine squared pi over 6. Sine squared pi over 6 has a numerical value, so we write minus 1/2 squared, so minus 1/4. To find the range, it might be helpful to sketch the base function, so sine x, and then draw each function transformation. The range of sine x in the given domain is from 0 to 1 inclusive. The range of sine squared x is also from 0 to 1, because we don't have any negative values that will become positive when we square them. Now we can add on the vertical transformation to sine squared x, so that's minus 1/4, and all we have to do is shift the whole function down 1/4 of a unit. So our range would be minus 1/4 to 3/4, since we're just subtracting 1/4 from the minimum and 1/4 from the maximum. Part C also asks us to find the range, this time of function g, which is cosecant x plus pi over 6 times cosecant x minus pi over 6 over the domain 0 to pi. What we should do first is rewrite cosecant as 1 over sine. This way, we can actually see that part C directly builds off of part B. It is simply the reciprocal of function f. We can use the properties of inverse functions to figure out the range. First, we can graph the function f and then deduce what function g would look like. We know that reciprocal functions are undefined when the original function is 0. This means that any zeros in the function f will become vertical asymptotes in function g. The y-intercept of function g is 1 over the y value of the y-intercept of function f. The same goes for the y value of any local maximums and minimums. The left-hand side branch of function g would be sloping downwards because f is negative here. So g would be approaching minus infinity at the left side of the first vertical asymptote. G also has a similar behavior at the right side of the second asymptote. Meanwhile, the middle branch would look like an upward parabola because f is positive here. So now we have identified that the range consists of two intervals. One is in the negatives and the other is in the positive direction. We can first find the value of the local maximum of a function g. For this, we need to find the value of the local minimum, or actually the y-intercept of function f. By substituting 0 into x into the function f, we find that the y-intercept is minus 1/4. And next we can find function f's local maximum. We already found this information in part b, so the local maximum is 3/4. So now we can find the local maximums and minimums of the function g. So the y-intercept of function g is 1 over minus 1/4, so that would be minus 4. And the local minimum would be 1 over 3/4, so it's 4 over 3. Now we can combine our knowledge of the local maximums and minimums of the function and its behavior to find its range. So we get the range is from minus infinity, not inclusive, to minus 4 inclusive, in union with 4 over 3 inclusive, to positive infinity not inclusive. And I accidentally wrote the first part in reverse, so it should be minus infinity to minus 4 and not minus 4 to minus infinity. I also drew the intervals on the graph for easy visualization. But that's the answer, so that's it for this video. Thank you for watching, and I hope I helped you with this question.